Hello everyone, my name is Inusarabi Isa Bodmas. Here in this video, we are going to talk on stress-strain diagram. Stress-strain diagram, from the word stress-strain, is just a diagram of, or is a graph of stress against strain. This diagram is used to determine the general properties of material. For us to design this diagram or to plot the graph of the axis of stress against strain, a tensile test is generally conducted on a generalized test of material to obtain the relationship between the stress and strain. This is an important characteristic of a material. During this test, the uniaxial load is applied to the specimen or material and increased gradually. The corresponding deformation are recorded through the loading. The stress-strain material vary widely depending on the material, whether it is ductile or brittle. So after this test, the diagram is successfully plotted. As we can see in this diagram, after this test and we find the corresponding stress and strain, we plot the graph. So from point O to point A is a straight line. It's a straight line. So what do we notice by this? This is just a linear relationship, and this point A is what we call proportionality limit, because the stress is proportional to strain at this point. And then when we continue loading the material, then it will reach a point B. And then after we continue loading the material, it reach point C, and then we continue loading the material up to D and then up to E. So what do those points represent? So in this case, point OA is a linear relationship, and point B is what we call yielding. That's yield point. So that is from A to B is yielding, the material is under yielding, and the stress on this point is what we call yield stress. Yield stress. In some cases we call it strains of material. Strains of material, because after this point the material will not regain to its original position or its original shape and size. That's why it's called strains. That the stress of material, that often the loading, the material will not get again its original position. And under this we have two kind of yielding or yield point. We have what we call upper yield and lower yield. So this point B is upper yield and point C is the lower yield, and the stress on point B is what we call upper yield stress, and stress on point C is what we call lower yield stress. I can demonstrate. This is upper, and at this point is what we call lower yield stress, and the strain against or on those points is what we call, in this case we have what we call lower yield strain and upper yield strain, and at this point we have what we call lower yield strain. So that is about this point. And then when the material is continue loading, then it continue increasing until it reach point D, which is obviously known as maximum point, that the maximum stress and strain the material can offer before fracture. So this is what we call at this point, this is a maximum, and the stress at this point is what we call maximum stress or ultimate stress. So at this point we have what we call maximum stress or ultimate stress, and the corresponding strain is what we call maximum strain. Anyway, even though the strain in this point is not the maximum strain, because the material continue loading, the strain is also increasing. So from this point, that's point C to D, the material is under hardening. That is those material that we call strain hardening. They had large strain before fracture. So under this point we have hardening. So after D, the material is continue loading, and then it reach point E, we will call fracture. So this fracture, that is, or we can call it breaking point, that the material at this point will break or will fracture. So, and again, this point DE is what we call necking. That is when material is started losing its properties before fracture or before breaking. And all know that from this point C up to E is what we call plastic, because the material is into plastic region. When we say plastic, that is from the word plasticity. The material will not regain its original shape and size. Is the opposite of elasticity. So elasticity is only limited to the point C or B, depending on the types of material. That is, it's only limited to yield point. That is, above yield point, the material will not regain its original shape and size. That's why when we are referring to elasticity, we are saying when the elastic limit is not exceeded. So this yield point is what we call elastic limit, is the elastic limit of the material. So this is about this. Then we had some further explanation and different diagram to explain. Let's move on. So let us consider this diagram again. And in this diagram we can see it's very similar to the new one. So the only difference is this another dotted line, and this is the indication of the new region of the material. When material is exceeding its elastic limit, that is a yield point, that this point, maybe it increases to another point. So while it is coming back to its original shape and size, you can see it will not follow its original path, rather it follow a new path, which is this. Now, okay, so under this curve, the curve is unique for each material and is bound by recording the amount of deformation as usual at the distinct interval of tensile or compressive loading. As the stress increase, initially hooks low obey. The stress-strain relationship for this material is linear and elastic, just before plastic is reached. When the limit of proportionality, that the elastic limit, beyond this small section, nonlinear behavior is started. So after the yield strength, the material enter the plastic region, which means that the stress of the wire is permanent of the material. For example, assuming this is a wire, yes. So in this case, we have explained all the section in the previous diagram. The only issue is this dotted line. So this is when the material exceeds its elastic limit. The material will not follow its original shape or its original path, rather it changes the path, which is this. So this is a new point, that's a point B. So that is the implication of this. And this is fracture point, or you can say breaking point. So it's all the same. So let us move to the last section of this. So in this case, we're going to see some feature of different material and that stress-strain diagram, because each material exhibits its own property while undergo loading, recording its corresponding stress and strain. So after this is occurred, we can see that always the brittle material follow the path like this first. That is, it has high stress well, the strength is very low. This is from the fact that brittle material is not exhibited large strength. It's a material that exhibited little or no yielding stress, no yield at all. What we mean by this is, when you apply a force on the brittle material, for instance chalk, then or wood, it will immediately break when you apply a large amount of force without increasing the extension or without extending. So that is brittle material. That is any material that exhibited little or no yielding. Then the next is what we call strong material. We can have a strong material which is not ductile, because a ductile material has its own property. But for ductile material, you can see it has high stress but low strength, but not as small as the brittle material. It has little yielding. It has undergo yielding, but not that of ductile material. And for ductile material is a material that exhibited large yielding before fracture. As we can see, this is under yielding, this is this up to this point, then it will now start it yielding, necking up to the breaking point. So ductile material is a kind of material that has large yield stress before fracture. And the last material we can have what we call a plastic. A plastic is a material that exhibited no yielding, no proportionality, no limited the strength. For instance, when it start loading, it will just go to directly to the fracture. That is the breaking point. It cannot regain to its original shape and size, and it cannot extend. That's why it is plastic. So a material that exhibited very small elastic region. So from here we can see from this point or to this point is just the elastic limit of the material. So after loading, it undergo the way it follow. So that is all about the stress strain diagram of the material. We have many material to analyze, but we leave it here. Maybe in the next video we are going to provide the other material like straight hardening material, and we have what we call viscoelastic material. That is the material that exhibited both viscous and elastic property. So we have a lot of material to study. So if you have any question, do not forget to forward it to us. We are here for you. Thank you very much for bearing us. I look forward to seeing your question and comments.